Today we're going to be talking about linear dependence of vectors. So what does that mean? That means, can we write vector C as a linear combination of two other vectors, so A and B there? In other words, can we scale our vectors A and B by a factor m down there for A and n for B? Can we scale those two vectors so that they're equivalent to vector C? So it's best to do this through an example. So if we take A as a vector 3i plus 4j and B as a vector 2i minus j, is it possible to scale A and B so that they become vector C, I minus 5j? So in this first example, we want to see if we can write this vector C, I minus 5j, as a combination of these two vectors. So can we scale vector A and vector B so that they add up to vector C? So are there values for m and n that exist? Okay, so the way we have to do that is we'll write out the whole equation. Okay, so vector C, now that's I minus 5j, and we want to see if that equals m of vector A, which is 3i plus 4j, plus n multiplied by vector B, which is 2i minus j. So the way we do this is we're going to equate the coefficients. Now on this side of the equation, we've only got one I here. So we can write an equation with all the i's here. So this one will expand out to become 3m times I, and this one will expand out to become 2n times I. So we want the 1i from this side of the equation to equal 3m plus 2n. Okay, we'll call this equation 1. And the j's, we do the same with the j's. So minus 5 on this side equals, now m multiplies by 4j, so we end up with 4m minus j times n, so we end up with minus n. Okay, that becomes equation 2. Okay, so solving this simultaneously, if we rewrite equation 2, so from equation 2 we end up with n equals 4m plus 5, rearranging this. So I've moved the n to this side and added the 5 to this side, so it's just a rearrangement of that formula. Okay, and then substituting into equation 1, so we'll sub it into 1, so subbing into 1. So this n is now going to replace this n here, so 4m plus 5 is going to go in here. So if we have 1 equals 3m plus 2 times n, which is 4m plus 5, so 4m plus 5, like that. And then we just have to do a little bit of algebra to solve for what m must equal. So how many m's do we end up with on this side? We've got 3m, 2 times 4m, that's 8m. So 3m plus 8m, that's 11m. And then 2 times 5, that's 10. So plus 10, that has to equal 1. So what does m have to equal for that to equal 1? So if we minus 10 on both sides, then divide by 11, we end up with m equals negative 9 divided by 11. So that's our fraction, but a value for m. So now what we can do is substitute this m back into our equation 2 here and solve for n. So if we put m back in, so we've got n equals, that's 4 times m, so that's going to be 4 times m, negative 9 on 11, so negative 9 on 11 plus 5. If we simplify this, what does that equal? So 4 times negative 9, that's negative 36 over 11, okay, plus 5, so 5 with a denominator of 11, that's 55 over 11. Okay, so adding up those fractions, what do I get? 55 minus 36. That gives me n equals 19 over 11. Okay, so now we can say that if A and B are scaled by these amounts, they can come out to be vector C. So these vectors are linearly dependent. Linear independence. Linear independence just means when a set of vectors are not linear dependent. So if you can prove that they're not linear dependent, then they are linearly independent. So an example of this might be if we've got a 3D vector like here. Notice we've got the k vector down there as well. So 3i plus 4j plus k for vector A. Vector B, 2i minus j minus 3k. And vector C, I minus 5j plus 5k. Now for the second example, we're trying to see if these vectors C, A and B are linearly dependent, and if they're not, they're linearly independent. So we can set up our equations by equating the coefficients like we did in the previous example. So in this case, we're going to get equation 1 equals 3m plus 2n. So I'll write that down. 1 equals 3m plus 2n. Okay, so that's equation 1. Equation 2, we get negative 5, just equating the j's, equals, what do we get, 4m minus n. Okay, equation 2. Equation 3, equating the k's, where we've got 5k here, equals m times 1k, so m, and n times negative 3, so we get negative 3n. Okay, our third equation. Now, to be linearly dependent, all three equations have to be satisfied by the m and n that we came out with. Now, the first two equations are exactly the same equations that we did in the previous examples, and we found that m was equal to negative 9 on 11, and n was equal to 19 on 11. So if this equation is satisfied by m and n, then these vectors are linearly dependent. If not, then we've found a contradiction and they must be linearly independent. Okay, so we'll just sub in the values for m and n and see if it equals 5. So does 5 equal negative 9 on 11 minus 3 times 19 on 11? Obviously not, it doesn't. We've got negative numbers here. These negative numbers are never going to equal this positive number of 5. So these vectors are linearly independent.